Thank you for having me. Myself, Sandamil Chelvi, Assistant Professor, Department of Computer Applications, Sri Kalishwari College, Sivagasi. And I am going to be speaking to you today about pipelining in computer organizations. To begin, in this session, we will discuss the types of pipelining hazards, and its advantages. So let us start. Pipelining organizes the execution of the multiple instructions simultaneously. It improves the throughput of the system, and in pipelining, the instructions are divided into the subtasks. Each subtask performs the dedicated tasks. The instruction is divided into 5 subtasks: instruction fetch, instruction decode, operand fetch, instruction execution, and operand store. The instruction fetch subtask will only perform the instruction fetching operations. Instruction decode subtask will only be decoding the fetched instruction, and so on the other subtasks will do. Example for pipelining concepts. Take a car manufacturing plant. At the first stage, the automobile chassis is prepared. In the next stage, workers add body to the chassis. Further, the engine is installed, then painting work is done, and so on. The group of workers, after working on the chassis of the first car, don't sit idle. They start to work on the chassis of the next car, and the next group take the chassis of the car and add body to it. The same thing is repeated at every stage. After finishing the work on the current car body, they take on the next car body, which is the output of the previous stage. Here, though the first car is completed in several hours or days, due to the assembly line arrangements, it becomes possible to have a new car at the end of an assembly line in every clock cycle. Similarly, the concept of pipelining works. The output of the first pipeline becomes the input of the next pipeline. It is like a set of data processing unit connected in series to utilize process up to its maximum. An instruction in a process is divided into 5 subtasks, likely instruction fetch, instruction decode, operand fetch, instruction execute, operand store. In the first subtask, the instruction is fetched. The fetched instruction is decoded in the second stage. In the third stage, the operand of the first instruction are fetched. In the fourth, arithmetic and logical operations are performed on the operands to execute the instruction. In the final stage, the result is stored in the memory. Now, understanding the division of the instruction into subtasks, let us understand how the n number of instructions in a process are pipelined. Look at the figure. There are 5 instructions pipelined. The first instruction gets completed in 5 clock cycle. After the completion of first instruction, in every new clock cycle, a new instruction completes its execution. Observe that when the instruction fetch operation of the first instruction is complete, in the next clock cycle, the instruction fetch of the second instruction gets started. This way, the hardware never sits idle. It is always busy in performing some or other operations, but no two instructions can execute their same stage at the same clock cycle. Types of pipelining. There are 2 major types of pipelining. One is arithmetic pipelining, another one is instruction pipelining. Arithmetic pipelining. It is designed to perform high-speed floating point addition, multiplication, and division. Here, the multiple arithmetic logical units are built in the system to perform the parallel arithmetic computation in various data format. For example of arithmetic pipelining processor are Star 100, TIASC, Cray 1, and Cyber 205. Second one, instruction pipelining. In instruction pipelining, the number of instructions are pipelined and the execution of the current instruction is overlapped by the execution of the subsequent instruction. It is called instruction look ahead. Next topic is pipelining hazards. Whenever a pipeline has to stall due to some reason is called pipeline hazards. Below we have discussed three pipelining hazards: data dependency, memory delay, and branch delay. First one, data dependency. Consider the following two instructions and their pipeline execution. In the figure above, you can see that the result of the add instruction is stored in the register R2, and we know that the final result is stored in the end of the execution of the instruction, which will happen at the clock cycle T4. But the sub instruction need the value of the register R2 at the clock cycle T3. So the sub instruction has to stall 2 clock cycle. If it doesn't stall, it will generate an incorrect result. Thus, depending of one instruction on other instruction for data is data dependency. Next one is memory delay. When an instruction or data is required, it is first searched in the cache memory. If not found, then it is a cache miss. The data is further searched in the memory, which may take 10 or more cycles. So far, that number of cycles the pipeline has to stall, and this is a memory delay hazard. The cache miss also results in the delay of all subsequent instructions. Next one is branch delay. Suppose the 4 instructions are pipelined like I1, I2, I3 and I4 in a sequence. The instruction I1 is a branch instruction and its target instruction is IK. Now processing starts and instruction 1 is fetched, decoded, and the target address is computed at the 4th stage in the clock T3. But till then, the instruction I2, I3 and I4 are fetched in the clock cycle 1, 2 and 3 before the target branch address is computed, as I1 is found to be a branch instruction. The instruction I2, I3, I4 has to be discarded because the instruction IK has to be processed next to I1. So this delay of 3 cycles 1, 2, 3 is a branch delay. Prefetching the target branch address will reduce the branch delay, like if the target branch is identified at the decode stage, then the branch delay will reduce to 1 clock cycle. So this is all about pipelining. So basically the pipelining is used to improve the performance of the system by improving its efficiency. Thank you all.